Hello everyone. Today we discuss the mean value theorem. So we start with a definition. A function f from some interval I to the set of real number is said to have a relative maximum or minimum at some point C inside the interval I if there exists a neighborhood V around this point C such that f of x is smaller than or equal to f of C for all x inside this neighborhood. For the minimum definition, then we had to reverse the inequality, that is f of x is greater than or equal to f of C. So the relative maximum or minimum, they are also called local maximum or minimum, to illustrate the idea that this is a local behavior. You only compare the value of the function with a nearby. So to better illustrate this concept, please take a look at this figure. So in this picture, the function f has a relative maximum at the point C, that is f of C is greater than or equal to f of x for all x within a small neighborhood around this point C. However, if we go beyond that small neighborhood, then the inequality might not hold anymore. Indeed, we can choose, in this example, we can choose a point D such that f of C here is smaller than f of D. That's why it's called a relative maximum only, not a local maximum, as we saw earlier. Now, here is the theorem. Let's see be an interior point of the interval I at which f has a relative extrema, either maximum or minimum, if the derivative of the function f at this point C exists, then f prime of C must be equal to 0. So this is called the first derivative test in calculus. The proof of this theorem goes as follows. Without loss of generality, we assume that f has a relative maximum of this point C. Also, because differentiability implies continuity, we know that the function f is continuous at this point C. If f prime of C is not equal to 0, then either it must be bigger than 0 or it must be smaller than 0. We consider the first case when f prime of C is bigger than 0. Recall the definition of a derivative. F prime of C is essentially the limit of an expression. That is, it equals to the limit when x approaching C of the quotient fx minus fc divided by x minus c. In this case, the limit is bigger than 0. That is, there must be a neighborhood around the point C such that the expression is bigger than 0. That is because of the property of a limit. This function approaching a positive number, it means that within a small neighborhood around this point, the function must be positive. Then we have f of x minus f of c is equal to x minus c multiplied with this portion f of x minus f of c divided by x minus c for, and this is greater than 0 for any x bigger than c. If x bigger than c, then x minus c is certainly a positive number. Then you multiply this positive number with another positive number. That's why the product must be positive. That's why fx minus fc is positive for any x bigger than c, and within this neighborhood, x belongs to v. But that contradicts the fact that f of c is a local maximum. Remember, the definition of local maximum is that it is greater than any nearby. And here we found many nearby points such that f of x minus f of c is positive. That is, fc is smaller than f of x. So that's why there is a contradiction. And because the proof is by contradiction, we know that the initial assumption must not be true. That's why we can rule out the first case. For the second case, we argue in a very similar manner, just reversing appropriate inequality and also arise other contradiction. So both cases cannot happen. That's why f prime of c must be equal to 0. Right? There are only 3 different cases. F prime of c is 0, bigger than 0, or smaller than 0. Can be anything else. We already ruled out that it cannot be either bigger than 0 or smaller than 0. That's why it must be equal to 0. And that is the end of the proof. Now, here is a corollary. Let f be a function from some interval I to a set of all real numbers. Also, we assume that let me see what is the correct assumption here. Let's assume that the function is continuous. And suppose that it has a relative extremum at an interior point C inside the interval I, then either f prime of C doesn't exist or f prime of C is equal to 0. We can see that it follows immediately from the theorem above. Now, another consequence is called the Rolle's theorem. Let f be a function from some interval I from A to B to the set of all real numbers be a differentiable function on I and FA equal FB equal 0, then there is at least C inside this interval from A to B such that f prime of C is equal to 0. The proof here is quite intuitive. The idea is that because the value of the function do not change at endpoints, it means that if the function increasing, then it must decreasing. If the function decreasing initially, then it must be increasing eventually. That is, there must be some point that the function changes from increasing to decreasing or from decreasing to increasing. These points are actually corresponding to local extrema of the function. And as a consequence, because the function is differentiable, the consequence is that f prime, the derivative of the function at these points, must be equal to 0. Now we are ready to state the mean value theorem. Suppose that f is a function from some interval a, b to a set of real numbers is differentiable in this inside the interval. Then there exists at least one point C inside the interval, an interior point, such that FB minus FA equal to F prime C minus times B minus A. In other words, we have the quotient FB minus FA divided by B minus A is equal to F prime of C. So let's denote this equation. So why is it called the mean value theorem? Well, in order to make sense of this terminology, we need to recall something from calculus. The fundamental theorem of calculus says that the derivative of the integration of the derivative of function, integration from a to b of f prime dx is equal to the difference of this function evaluated at these endpoints. That is equal to fb minus fa. So with this knowledge, we can rewrite equation star in the mean value theorem as follows. The denominator here is essentially the integration of the derivative of the function from a to b. And then we divided that by the length of this interval, b minus a. In other words, the numerator here is the summation of all derivatives over that interval divided by the length of the interval. That's why it is the average of the derivative of the function in the sense. And we say that this average is actually realized by the derivative of the function at some point C. That's why it's called the mean value theorem. Now, another geometric interpretation of the mean value theorem is as follows. We recall that the quotient FB minus FA divided by B minus A is essentially the slope of the line segment connecting these points A, FA, and B, FB. On the other hand, F prime of C is the slope of the tangent line at some point C. So if we look at this picture, you see that the quotient FB minus FA divided by B minus A is essentially the slope of this line segment AB. Then the mean value theorem says that there must be a point C within this interval from A to B such that the tangent line of this point C is parallel to the line segment AB. Now the proof here is in the same spirit as many proofs that we saw earlier, but it's a little bit more involved. So we consider a function phi of x which is equal to f of x minus f of a minus the quotient fb minus fa divided by b minus a times x minus a. So phi of x here is essentially the difference between the function f of x and the function representing the line segment AB. So it measures the distance from the function f of x to this line segment. We verify that phi of a and phi of b are equal to 0. So phi of x satisfies the condition of both theorems. Just there is a point C within this interval such that phi prime of C is equal to 0. However, if we go back to the definition of this function phi of x, we see that phi prime of x, the derivative of the function, is essentially equal to f prime of x minus the derivative of the expression fb minus fa divided by b minus a times x minus a. F of a is a constant, so taking derivative of constant is equal to 0, and it doesn't contribute to our calculation. So this is equal to fb minus fa divided by b minus a. Again, this is a constant, so we only need to take the derivative of this expression x minus a. And the derivative of that expression is essentially equal to 1. So this is equal to fb minus fa divided by b minus a. So on one hand, the derivative of the function phi of the point c equal to 0. On the other hand, that is equal to f prime of c minus this number, this quotient fb minus fa divided by b minus a. That's why at the point c, f prime of c must be equal to this quotient. So that is the mean value theorem, the proof of the mean value theorem.